Hello, my name is Vivian Feig, and I'm a fifth-year PhD candidate working with Professor Zhenan Bao at Stanford University. I'm thrilled to have this opportunity to present my graduate research, which is focused on developing new materials design and patterning strategies to enable long-term bioelectronic interfaces. While electronic devices have increasingly gained interest for a variety of biomedical applications, the long-term interfacing of electronics with biological systems is limited by a severe mismatch in mechanical properties between conventional conductive materials and soft biological tissues. Traditional metal conductors like gold can be hundreds of millions of times more stiff than things like brain tissue. For bioelectronic implants, this severe mismatch results in an inflammatory response that ultimately causes glial scar encapsulation of devices and loss of functionality. This mismatch also makes it challenging to successfully incorporate electronics into regenerative therapies, where cells are known to be highly sensitive to the mechanics of their surrounding environment. To overcome this mismatch, hydrogels are a promising class of polymeric materials that possess elastic moduli comparable to soft tissues because of their high water content. Unfortunately, prior attempts to make hydrogels electrically conductive typically involved blending stiff conductive fillers into a soft and stretchable hydrogel matrix. This approach inherently results in a trade-off between conductivity and softness, so that gels that actually possess desired mechanical properties typically have very low conductivities of less than 1 Siemens per meter. We hypothesized that if we could form conductive hydrogel networks completely out of a conducting polymer, then we could deliberately design macroscopically connected networks for charge transport that would allow us to maintain a high water content without relying on a large amount of stiff filler to achieve high conductivities. To accomplish this, we leveraged the ability for a conducting polymer called P.PSS to form hydrogels from very dilute solutions of polymer and water. P.PSS is a two-component complex where P. can conduct charge across its conjugated backbone, and PSS acts both as a dopant and a way to disperse the insoluble P. in water. It is commercially available as an aqueous dispersion of 1 to 2 weight% and has been frequently used in the form of solid films and coatings because of its high conductivities and its good biocompatibility. When dispersed in water, P.PSS takes on a colloidal structure comprising dilute nanogel particles that electrostatically repel each other due to the negatively charged PSS groups. We found that increasing ionic strength could destabilize these colloids, resulting in a colloidal hydrogel where the storage modulus is directly proportional to ionic strength and where storage modulus exceeds loss modulus, indicating solid-like behavior. Interestingly, we found that certain ionic species that are known to enhance conductivity in P.PSS films similarly seem to enhance conductivity in these hydrogels. For example, our group previously found that the ionic liquid shown in the top right boosted P.PSS thin film conductivity by disrupting the interaction between P. and PSS, thereby allowing P. units to form conductive pi-pi stacking junctions amongst themselves. Similarly, when we compare P.PSS hydrogels made with this ionic liquid to ones made with simple salts found in phosphate-buffered saline, we can see that in both cases we can create very soft gel materials with storage moduli around 100 pascals, as shown on the rheological plot in the bottom left here. But the gels made with the ionic liquid possess significantly reduced impedance over all frequencies, as seen on the graph on the bottom right. This transition from a highly frequency-dependent impedance to one that stays relatively low and flat is also consistent with the transition from an ionically conductive material to a material that can conduct electrical charges at low frequencies as well. Thus, we argue that these ionic species transform P.PSS from a colloidal gel to a conductive gel with an extended pi-pi stacking-based conductive network. We also observed that this ionic liquid resulted in a relatively slow gelation process. We monitored gelation time by mixing P.PSS with the ionic liquid and measuring its storage and loss moduli on a rheometer. From this experiment, we saw that there was a 13-minute working window during which time the mixture behaves like a liquid, with loss modulus exceeding storage modulus. This gives us ample time to pour gel precursors into molds so that we can form arbitrary shapes, including these small pyramid structures shown here. So with electrical conductivity and favorable gelation kinetics for molding, we now have an all-conducting polymer network that dictates the electrical conductivity of our material. To then orthogonally tune mechanical properties like modulus and stretchability, we next hypothesized that we could use a secondary polymer network interpenetrated with the P.PSS network. As a proof of concept, we backfilled P.PSS hydrogels with acrylic acid monomers and a thermal initiator, which was needed because UV light does not effectively penetrate the opaque P.PSS gels. After initiation, the acrylic acid polymerizes into polyacrylic acid, resulting in conductive interpenetrating network hydrogels, or what we call CIPN. The benefit of this approach is that we can modulate the mechanical properties simply by tuning the secondary network. By just changing the monomer concentration and the ratio of chemical crosslinker to backbone monomer, we were able to tune the elastic modulus of our CIPN gels over 3 orders of magnitude, achieving stretchabilities of nearly 400% strain, all while maintaining high conductivities within the same order of magnitude around 10 Siemens per meter. Moreover, because the conductive component is formed into a macroscopically connected network, and because there is plenty of free volume in the hydrogel to accommodate strain, our CIPN can maintain conductivity even when stretching to 100% strain over 10 cycles, as shown on the bottom right. Despite these promising properties, for this material to be used in bioelectronic devices, we still needed a more scalable and versatile patterning method than the molding-based fabrication that we had used to develop the material. To achieve this, we developed a new patterning method called electrogelation, which relies on the controlled electrochemical oxidation of a sacrificial metal layer. Oxidizing this layer in the presence of a P.PSS electrolyte generates metal cations that induce gelation of P.PSS at the interface. This phenomenon enables us to take advantage of much more well-established techniques for patterning metal thin films, including evaporation through a shadow mask. Using that pattern as a working electrode in an electrochemical cell with P.PSS solution as the electrolyte, we can then use electrochemistry to transform the sacrificial pattern into a patterned conductive hydrogel. Here again, gelation kinetics play an important role. Compared to the ionic liquid, gelation of P.PSS in the presence of copper ions happens nearly instantaneously, such that we cannot even see a crossover on the rheometer, which is shown on the bottom left here. This allows the sacrificial metal pattern to be transferred to the resulting hydrogel with high fidelity, because the ions do not have enough time to diffuse away from the surface before gelation occurs. Therefore, we're able to use electrogelation to pattern P.PSS hydrogels into fine feature sizes down to 100 microns, while maintaining the favorable porosity of the hydrogel. Moreover, because electrogelation initiates gelation at the substrate surface, we can easily use this method to pattern onto curved surfaces or to generate conformal hydrogel coatings onto arbitrary three-dimensional structures. The method is also compatible with making conductive interpenetrating network gels, as the patterns can be backfilled with secondary network monomers and polymerized to create fully stretchable embedded conductive patterns. To summarize, we have drawn upon our understanding of P.PSS solution properties and insights into the manipulation of P.PSS thin films to fabricate all P.PSS hydrogels that combine electrical conductivity with a high water content and therefore with tissue-level elastic moduli. We next use interpenetrating polymer networks to orthogonally tune mechanical properties like stiffness and stretchability. And finally, we used electrochemistry to create a new patterning method that will broaden the opportunities for this material to be used in next-generation bioelectronic devices. I'd like to thank all of my collaborators on these projects and Professor Jianan Bao for her invaluable guidance throughout my PhD. I'd also like to thank my funding sources, the National Defense Science and Engineering Graduate Fellowship and Stanford BioX. And finally, thank you to the symposium organizers. I'm honored to be included in this symposium and appreciative of your incredible job of adapting to unexpected recent events by hosting these talks online. Thank you all for your attention.